Hello, and thank you for watching this virtual tour at the Natural History Museum of Los Angeles County. I'm Dr. Kirk Fitzhugh, one of the curators here at the museum. I'm a marine biologist and I conduct research on the evolution of segmented worms called polychaetes, which are found in all the world's oceans. For conducting my research, the museum houses an important piece of equipment that I and other museum scientists routinely use, called a scanning electron microscope, or SEM for short. Our SEM is not currently on display for the public to see, but you've probably seen photos that have been taken using an SEM, like those shown here, of microscopic animals, plants, and other objects. Such images are striking because of their clarity and having an almost three-dimensional appearance. Today, I'd like to tell you more about our SEM, what it looks like, some basics on how it operates, and how it's unlike the microscopes you're probably familiar with. In many ways, knowing how scanning electron microscopes operate is just as remarkable as the images they produce. So I hope you'll enjoy this presentation. Our eyes have a good ability to see small objects. For instance, the naked eye can see objects as small as the thickness of a human hair. But even though we can see tiny objects, our ability to actually see details of those objects can be very limited. That's why microscopes are so important. A microscope is an instrument that enables us to see objects that are too small to be adequately seen with the naked eye, or that are not visible at all. In other words, microscopes enhance our visual abilities. There are two goals we want to achieve with the use of microscopes: magnification and resolution. Let's see what we mean by these two concepts. First, magnification. This is the process of enlarging the apparent size of an object, making an object appear larger than it really is. This is accomplished by passing light from an object through a glass lens or series of lenses into our eyes. Using a light microscope, and depending on the quality of the microscope, we can magnify objects from as little as 5 times up to a magnification of about 1,000 times. What's important to consider is that even with all the advances that have been made in light microscopy over the last several hundred years, the maximum magnification that can be achieved is no more than about 1,000 times. As we will see in a moment, this is because of certain limitations of the properties of visible light. The other important goal of microscopy is what we call resolution. Do you see this tiny spot outlined here? Let's see what happens if we magnify that area. With magnification, we find in fact there are 2 objects rather than 1. In other words, with magnification, we have increased our resolution. Resolution is the ability to distinguish 2 objects from one another. But resolution not only depends on magnification, but also the wavelengths of light. Let's consider the following analogy to describe what I mean here. Let's say we want to illustrate the shape of a person's hand. Using large balls in the example on the left, we get a very poor representation of the hand. But with much smaller balls surrounding the hand, we have a much more accurate outline. Just as the larger balls offer less resolution of the hand compared to much smaller balls, wavelength is critically important for attaining resolution of objects in relation to magnification. Let's consider wavelength in relation to light microscopes and scanning electron microscopes. Visible light is just one form of electromagnetic radiation, and all electromagnetic radiation travels as waves. We characterize this energy based on the wavelengths of these waves. For instance, our eyes are only capable of perceiving the narrow range of wavelengths that we call visible light. Longer wavelengths of electromagnetic radiation, such as infrared, microwaves, and radio waves, are beyond our ability to see. Similarly, wavelengths shorter than visible light cannot be directly observed, such as ultraviolet, X-rays, or other radioactive energy. Electrons, which we will see later are used to produce images in scanning electron microscopes, have a much shorter wavelength, considerably shorter than wavelengths of visible light. This means electrons can achieve far greater resolution and magnification of objects compared to any light microscope. Returning to light microscopes and magnification for just a moment, I want to mention that there are two basic types of light microscope that we use. One is called the compound microscope. These are usually capable of producing magnifications ranging from about 40 times up to a magnification of about 1,000 times. Light is passed or transmitted through an object. Then that light passes through sets of glass lenses to the eye. The other type of light microscope is called a dissecting or stereo microscope. These have a more limited range of magnification and usually rely on light being reflected off objects, and then that light proceeds through lenses to the eye. As we will see later, scanning electron microscopes produce images in a radically different and quite ingenious way. The first scanning electron microscope, or SEM, shown here, was invented in 1937, but SEMs didn't become commercially available until the 1960s. As I've said already, SEMs use electrons as opposed to visible light to produce images. And since the wavelengths of electrons are far shorter than visible light, the images produced by SEMs are grayscale images, not in color. And because of the short wavelengths of electrons, that means we can achieve much higher magnifications and far greater resolutions of microscopic objects. Since electrons are used in an SEM, it's necessary that the interior of the microscope and the objects observed be in a high vacuum. The reason is because air molecules would block the movement of electrons in the microscope. And if biological specimens are going to be viewed in a vacuum, they first have to be dehydrated so that the interior of the microscope isn't contaminated with water or organic materials. We use special techniques to remove water from specimens without their shrinking or becoming deformed. And finally, while light microscopes have the ability to view the interiors of small translucent objects, scanning electron microscopes only allow us to view the surfaces of objects. Unlike visible light, electrons in an SEM cannot penetrate objects. This is the scanning electron microscope we use at the Natural History Museum of Los Angeles County. Let's begin by identifying the major components that we see here. First, the main part of the microscope itself is outlined here. The microscope sits atop a cabinet that contains one of the vacuum pumps and some of the instrumentation for the scope's operation. The right side has the controls for manually operating the microscope, display monitors for viewing, and computers for operating the software. The device shown in the upper left, attached to the microscope, is called the EDS, which stands for Energy Dispersive X-ray Spectroscopy. This is an instrument that can determine the compositions of objects based on the X-rays emitted by those objects while in the microscope. In our museum research, EDS is important for some of our studies of organisms, for characterizing some minerals, and in some cases for examining archaeological artifacts. Near the end of this presentation, I'll mention EDS again in relation to my own research. Let's look a little more closely at the exterior of the microscope. The lower half of the microscope is called the chamber. This is where the specimens are placed that are going to be viewed using the microscope. The door opens and allows for inserting or removing objects. The upper part of the microscope is called the column. There are tubes extending from the column and chamber that lead to the vacuum pumps, which are used to create the vacuum in both the column and the chamber. Let's now look at the interior of the column and chamber. At the top of the column, there is a high voltage cable. This cable connects to a device called the electron gun. At the lower end of the electron gun is a tiny filament. When high voltage is passed through this filament, usually between 10,000 and 30,000 volts, high energy electrons are released from the filament. Those high energy electrons then proceed down the column as an electron beam, eventually coming into contact with the sample in the chamber. The electron beam needs to be focused to a very small point when it hits the sample. This is achieved by controlling the beam diameter with what are called condenser lenses located in the column. These are not lenses made of glass, but instead they are donut-shaped electromagnets. Keep in mind that electrons are negatively charged particles, so their movements can be controlled by magnetic forces. The narrow beam of electrons hitting the sample in the chamber also need to be controlled such that the beam rapidly scans back and forth over the surface of the sample. This scanning process is controlled by what are called scan coils located in the column. This is why this type of microscope is called a scanning electron microscope. Another important part of the microscope is this tube-like device that extends into and outside of the chamber, called the secondary electron detector. I'll describe this detector in just a moment. If we open the door to the chamber, we see what is called the stage, upon which is located a holder where the specimen or sample can be placed. Let's look at this area a little more closely. Here, we're looking straight down on the opened door and the stage. The controls on the outside of the door allow for changing the position of the stage and specimen when it's in the chamber, so that the specimen can be viewed from any angle. We're now looking directly into the opened chamber. You can see the stage and sample holder. This entire assembly slides into the chamber when the door is closed. And the top of the chamber, you can see a cone-shaped structure. This is called the final condenser lens, which also controls the electron beam. The electron beam, indicated by the red arrow, extends into the chamber from the bottom of the condenser lens. Keep in mind that this electron beam is continually scanning, one line at a time, over the surface of the sample in the chamber. I mentioned earlier that the beam produced by the electron gun is a stream of high-energy electrons. When these electrons hit a sample, they cause the release of low-energy or secondary electrons from the surface atoms in the sample, indicated by the green arrows here. These secondary electrons are easily attracted to the magnetized end of the secondary electron detector that extends into the chamber. It is at this point that the process of image formation of the sample begins. Unlike forming images with a light microscope, obtaining images with an SEM is quite fascinating. As a reminder, the secondary electron detector extends into the chamber as well as can be seen extending outside the chamber. Let's look at how the secondary electron detector converts the pattern of secondary electrons into signals that can be converted to images on the display monitor. Here we see secondary electrons being attracted to the entrance to the secondary electron detector. Looking at the detector itself, when the secondary electrons enter, they strike the surface of what is called a scintillator. With each strike of each electron, the scintillator produces a ray of light. These light rays then move into what is called a photomultiplier tube, which contains a series of mirrors that amplify the light signal. That amplified light signal is then converted to an electrical signal. And that signal is then sent to a display screen for viewing the specimen. So, unlike what you see using a light microscope, images produced by the SEM are actually representations of the distributions of secondary electrons being emitted from a specimen or sample. That's quite a remarkable process, isn't it? Summarizing what we've been talking about regarding image formation with SEM, images are formed using electrons, not visible light. Since the wavelengths of electrons are much shorter than visible light, SEM images do not show color. Rather, images are grayscale, and the different shades of gray reflect the intensities of the secondary electrons coming off the scanned sample. This means areas in an image that are more white are due to more secondary electrons coming off the sample, while the darker areas in the image are due to fewer secondary electrons. You will, however, commonly see scanning electron microscope images that are in color, like these pollen grains shown in the photo on the right. All color SEM images have been artificially colored. The actual original photo is shown on the left. Just like image formation in the SEM is not what you might expect, magnification is also not the same as seen with light microscopes. I mentioned earlier that lenses in the SEM are not made of glass, but instead are electromagnets used to control the electron beam. So, how are different magnifications achieved with SEM? It's actually quite simple. Magnification is just the ratio between the area that is scanned and the display of that scanned area on the display monitor. Let's look at an example to show you what I mean here. This is an image of a snowflake in an SEM. And yes, there are some models of SEM that have cryogenic chambers for viewing frozen objects. The snowflake in this photo is magnified 93 times. Let's say I want to increase magnification of the area outlined in yellow. Unlike a light microscope, when you would have to change lenses, with an SEM, all that is required is to reduce the area scanned to within the yellow box. That change in scanned area then results in an image of higher magnification. And this same process can then continue further and further still, eventually far exceeding magnifications possible with light microscopes. I'd like to briefly mention how SEM plays a role in my own research. I study very small segmented worms that live in all the world's oceans. These worms are called polychaetes. I examine their morphology, describe new species, and study their evolutionary relationships. Nearly all polychaetes need to be examined using microscopes, and scanning electron microscopy is especially useful when dealing with very small translucent specimens. SEM allows for examining surface details along the body, such as on the photograph on the left, and at higher magnifications, such structures as the bristles that are located along the body, like that shown in the right photo. The high magnifications provided by SEM are often more informative than what light microscopes can provide. For instance, I often need to examine the shapes of sperm cells produced by polychaetes, as shown here. The highest magnification with a light microscope can't achieve the magnification and resolution shown here. Recently, I've been using EDS, or energy dispersive X-ray spectroscopy, on our SEM to analyze the composition of the bristles on a group of polychaetes called fireworms. When high-energy electrons hit an object in an SEM, in addition to producing secondary electrons, X-rays are also emitted. Different types of X-rays are produced depending on the elements in the specimen, and EDS analyzes those X-rays. In my research, I discovered that the bristles of fireworms are composed of calcium phosphate, a finding that has not been reported before for polychaetes. And finally, we hope one day to have our research SEM on display so the public can watch it in operation by museum scientists. This will provide a unique opportunity for visitors to see an important facet of ongoing research. An SEM on display and in operation in conjunction with an exhibit on the basics of microscopy will open a window into some of the important technologies used in many fields of science. And just as many schools are now offering hands-on experiences with SEMs, there are multidimensional education opportunities possible in a museum setting. So, thank you for going on this virtual tour with me today, covering some of the basics of microscopy and scanning electron microscopes. I hope you had a great experience, and thank you again.